So we are examining the detection of heteroskedasticity, and we want to test if there is heteroskedasticity. Okay, how do we know? There are two methods that we can know. All right, two methods. The first one is the formal test. The second one is the informal test. All right, but let me start with the informal test. Okay, informal test, like we did in autocorrelation. For the informal test, you can plot a graph. Okay, plot a graph, all right, of your dependent variable y against the square of your error term. If you plot that graph and there's a similar pattern, then you can conclude that there is heteroskedasticity. Okay, what do I mean? Um, you have your graph probably between the error term square and your y estimated. Okay, if you plot the graph between your error term square, okay, and your yt at, and there is a similar pattern, probably it's following a similar pattern, then you can conclude that there is what? Also heteroskedasticity. But if it's not following a unique pattern, either this nature or this nature, or is following this nature, if it's not following a unique pattern, then you can conclude that there is no heteroskedasticity. That is the informal um, method. Okay, that is the informal what method. Under the formal method, that is the graphical method. So let's look at an example. Okay, so I would be sharing this is the data we used, all right, in our previous example. Okay, the data of Nigerian economy from 1981 to 2019. Okay, and that data has to do with GDP, government expenditure, investment, trade balance, inflation, and exchange rates. Okay, so I'm going to estimate this model. Remember, I will estimate the model. My y there is GDP. Okay, then other variables are government expenditure, investment, trade balance, inflation, and exchange rate. Okay, so what am I doing? I am estimating that equation. What is my equation? The equation is what? GDP, okay, is a function of what? Investment, all right, government expenditure, okay, trade balance, okay, inflation, okay, exchange rate, okay. Remember, using graphical method says estimate this model, generate your error term. When you generate it, square this error term, okay? When you square the error term, also generate your GDP at, all right? Generate your what? Your GDP at. Find the relationship between these two. If there's a relationship between the two, then there is heteroskedasticity. And if not, there is no heteroskedasticity. Okay? So let's conduct that particular test. So what do I do? All right. I would copy my data as usual, and I will take it to eView environment. I copy my data, okay? And then I will take it to eView environment. We can see this is my eView, okay? Control N to create a new series, 1981 down to 2019, all right? And then I will paste down my data, okay? I've pasted. So these are my data, all right? So I'm sorry, you need to learn all of that. I believe you should have been able to do that. So I will estimate my equation. My equation is log GDP if is a function of beta 0. Other variables are what? Exchange rate, okay? Um, log government expenditure, okay? Inflation, log investment, and then trade balance. I estimate my result, okay? Oh, sorry, I need to log, I think trade balance, I need to log it. I don't know if there's a negative value. Okay, there's a negative value, I can't log trade balance. So this is my what? Result, okay? This is my result. So what do I do? I will go to where I have receipt. That's where my error term is. It's automatically generated. And I will copy my error term. Okay. I will copy my error term, copy it. Okay. And I'll take it to what? The Excel environment. I'll take it to the Excel environment. All right. Then I will paste my error term. So this is my error term. I will paste it. So I have my error term estimated. This is mu t. But remember, I'm looking for mu t square. So that means I will need to have mu t square. And that will be equals to what? This, all right, square. And I'll square it. I drag it down. I'm sorry, please learn all of this. So this is my error term square. I have estimated it. This is my error term square. The next thing is for me to generate my GDP at. Okay, that's the next thing for me to do. And to generate my what? My GDP at. Okay, so how do I generate my GDP at? Okay, so I will now need to generate my GDP at. Okay, I just needed to bring myself up to speed on that. Remember, my estimated result is where's my estimated result now? My estimated result. This is okay. Let me re-estimate. Sorry, let me re-estimate. Log GDP constant log government expenditure inflation log INV and trade balance. Am I correct? Then exchange rate, yeah, exchange rate, GDP, government expenditure, inflation. Okay, so this is the result again. All right, I will go to view. You will see the actual, fitted, and residual table. I will choose the table. Look at it. The actual is all of this. This is the actual. You know, when you log your GDP, which is your Y, your GDP was very large. So when you log it, it's reduced. So this is the actual. All right. And then this is the fitted. The fitted is what I need. This is the fitted. This was the residual that I picked. If you remember, the residual that I picked in the first one. So I will copy the fitted. All right. When I copy it, I take it to my Excel environment. All right. I'll take it to my Excel environment and then I will paste it. This is it. This is fitted. Sorry, let me paste it up. This is fitted. That means this is YT at. Okay. YT at. All right. Then I will copy my years. Remember, my years is from sorry, my years is from 1981. Okay, down to 2019. All right. So I will copy. Okay. But aside that, I will now plot this graph and see the pattern it follows before I can conclude if there is heteroskedasticity or not. So look at the pattern. Can you see the pattern? I need somebody to respond to me.
Yes.
Okay.
Yes, sir.
So let me fit a line graph and let's see how it is. Let me fit a trend on it and let's see how it is. Look at it. You will see that at the initial stage, all right, you will see that there is no unique pattern this is following. Or can we conclude that the unique pattern? They are all
No.
clustered around. So you will see that there is no unique pattern this is following. So we can say that, well, there is no heteroskedasticity by looking at what? The pattern of the relationship between our error term squared and the YT. We can conclude on that. All right. Do we understand that?
Yes.
Yeah? Do we understand that? Solomon, are you here? Can you hear me?
I'm here, sir.
Okay. Do we understand that? Nobody's talking again. Somebody should ask question. And if you don't understand, let me know.
So, good morning, sir.
Yes, sir.
Sir, I don't know. Can we, probably the exam is historical. And how can we apply this thing historically? That's the book. I think that's where everybody's mind.
Don't worry about
No,
exam.
because
Wait, let me ask you a question. Do you understand what I did?
understand the pattern. We
Eh?
checking what you showed us. I
Yes.
understand the pattern from what I'm seeing.
See,
But
on that,
I'm just
wait, you don't be too critical about the exam. Eh? Let me just take you to speed traditional y at. You remember your yt is equals to beta 0 at plus beta 1 at xt. All right?
Yes.
You remember you will have x, y, abi. You will have x, y. You will have x square, abi. You will estimate. You remember beta 0
Yes.
at is y bar minus beta 1 at x bar. You remember?
Yes.
By that time you estimate, maybe beta 0 at, you've estimated it, beta 0 at is 2.4, for example. Abi? Then you remember that beta 1 at is n summation xy over summation x square. You remember? Please do
Yes,
respond.
sir. Yes, sir. Yes, sir. Yes, sir.
You know, when you now estimate it, beta 1 at will now be 2.1, maybe for example. Okay. Remember, you use all this formula to do it. Beta 0 at is y bar minus beta 1 at x bar. Beta 1 at is summation x y
XY.
over summation x square.
X.
Yeah. So if you have done all of this, remember there's a time they'll not tell you, or you find your fitted y. You will now say y at. That's when you now be saying it's equals to beta 0 at is what? 2.4 plus beta 1 at is what? 2.1. Then x. You will now say for this first one, assuming x is 4, 5, 9. For this first one, it will be what? 2.1 times x times 4. Abi, that's 8.4.
Yes, sir.
8.4 plus 2.4. That's 10 point what? 4.
Yes.
what happened again now.
Somebody is talking there, please. I'm begging you. I'm begging you. Then the second one again, you will say when x is now 5, that's for the second one. X is now 5 times 2.1, that's 10.5. 10.5 plus 2.4, that's what? 12.9. You remember when you will continue that thing? Can you remember?
Yes,
Yes.
sir.
That is your y fitted. That is your what? That's your y fitted. Remember, after that, you now say your error term at is equals to y minus y at. Can you remember?
Yes.
So this is that error term I got. I now squared it. This is that fitted, which is y at I got and squared it.
Okay.
Do you understand it
Thank
now?
you. Yes, sir.
Okay. So there's no magic. So the basic thing there, that's why, in abroad, nobody is going to be teaching you summation here and the summation. No, 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 no. Softwares are there to do it for you. So that software will generate it instantly, bah, 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 and then you proceed. Do you understand that now?
Yes.
Okay. All right. So let me now continue. So that's number one, informal method. Under that informal method, we also have another one, the second part. That one is because of the nature of your data. There will be heteroskedasticity. So under this scenario, we say that heteroskedasticity is peculiar to a cross-sectional data, because most times in cross-sectional analysis, heteroskedasticity is peculiar, is there. Remember, for cross-sections, the structures are different. That's cross-section. Example, we are looking at the income pattern of undergraduate students. Of course, within Unilag, we have those that are from low income class, middle income class, upper income class, of course, and we have the wealthy. So if all of us are in the same class, the structure of a group of set of people will be different from others. Remember when I gave an example, when I said, assuming we want to understand we want to conduct a test, maybe to understand the consumption, the terms of consumption of undergraduate students, for example. All right. And then Solomon decides to administer his own data. Ore decides to also administer his own data. Solomon chose group of people. Ore chose group of people. But Ore's group of people are the rich girls, those that parents give them uncles, uncle, aunties, auntie, give them. Solomon also, of course, follows those that they don't have uncles or uncle, aunties or auntie, all right? They just have their parents that give them. You will see that the structure of the two will be different, and there will be heteroskedasticity without even disturbing ourselves, because the pattern used under Ore are a group of high-income people, and the pattern used for Solomon are the group of low-income earners, although they are from the same population, although they are undergraduate students. But because of this category of people, there will be heteroskedasticity associated with the result. So under the informal method, just examine the nature of the data. From the nature of the data, you can easily conclude that there is heteroskedasticity. You don't need to negotiate about it. From the nature of that data, you will just conclude that, there's heteroskedasticity from that nature of the data. Do you understand that now?
Yes, sir.
All right. So the third one now is let's now move to the formal ways of detecting. That's when we actually conduct a test. The formal ways of detecting is when we conduct some tests. The first one is pack test. Pack test. Pack test. That's the first one. All right. And what did Pack say we should do? Okay. Pack said we should estimate a model. All right. And that model should take this form. Pack said Estimate the log or ln of your error term at square. Okay, is there any name given for the second informal method? That one is based on the nature of the data, or nature of the variable you are considering, the nature of the problem. That's what they call it, nature of the problem. Okay, so under the PAC test, PAC said estimate log of error term at or ln mu t at to be equals to beta 0 plus beta 1. Okay, log of this PAC is assuming that there is two variable regression, that is y is a function of x. That's what PAC is assuming, that there are two variable regression, just y is a function of x. So PAC said estimate ln ut at square to be equals to beta 0 plus beta 1 ln xt. Estimate this model. When you estimate this model, if this beta 1 is statistically significant, then you conclude there is what? Heteroskedasticity. But if beta 1 is not statistically significant, then you conclude that there is no heteroskedasticity. That's PAC test for you. Are we following?
Please come again, sir.
Yes, sir.
PAC test says estimate your model first. You estimate your model. Okay, y equals to say alpha plus alpha 1 x t. Estimate this model. When you estimate it, generate your error term. Okay, when you generate your error term, square it. When you square it, log it. When you log it, that becomes this. Then estimate again this squared log of your error term as a function of the log of xt. When you do that, if this beta 1 at is statistically significant, then you conclude there is heteroskedasticity. But if not, then there is no heteroskedasticity. Are we together?
Yes.
Okay. So
Yes,
from
sir.
our example, okay, from my example, I can just let me call GDP my y, let me call government my x. Abi? So I will take these two to estimate the first model. Y is a function of what? X. I take it to my Excel environment. All right, I take it to my Excel environment. Okay. I delete all of this and then I create a new one. Don't bother about all of this I'm doing. Just know I want to estimate a model. You already know the formula of how to estimate models. Okay. So I paste it. So remember, I will now estimate this model. Okay. I estimate it log y because the values are large. So I need to log it. Log y, my constant log x. So I estimate it. That's my result. Okay. I come and pick the error term. This is the error term. I copy the error term. Leave all of these processes. I've just estimated my result and I've copied the error term. Okay. So I copy the error term. I can paste it here. Let me paste it in sheet 2. I paste my error term. So this is my error term, mu t. Remember, but remember I'm looking for log of mu t square. So I'll first of all square my mu t. All right, I'll square it first. And when I square it, I have all of this. This is the square. Okay, I've squared it. Remember, I'm looking for log or ln, log, anyone you use. You can use log, you can use ln, log of mu t square. So for me to log it, I'll just say type equals to ln this. I'll log it. Okay, so I've linearized it. just log your variable. You will know how to do that using normal line. I can use the line. So I've linearized my error term square. Remember, the equation says estimate your lin mu t square together with what? Your x. Where's my x? This is my x. But remember, it is the log of what? It is the log of x. You can remember, it is the ln of x, okay? So I can paste that x here. Then remember, I will linearize it. So this will become ln of x. That's equals to this ln of this, okay? I linearize that as this. So I have estimated my model. Let me take my y here so that you will see everything. Let me take my y here. All right. I have estimated my model. The first thing I did was to estimate y as a function of x. When I did that, I generated my error term using your normal formula. This was the error term. The next thing is for me to square the error term. I squared the error term. All right. The next thing is for me to linearize the error term. I linearize the error term. That's ln of the error term. Then the next is for me to do the ln of x, this ln of x. So I will now estimate this model. Okay. So I will take it to my Excel environment, my eView, sorry, to estimate that model. Okay. Let me delete this one I have before. Then I estimate the model 1981 down to 2019. Okay. I estimate the model. All right. So I'm going to estimate. And what am I estimating? Ln, remember, ln ut square constant ln x. Look at it. You see, from the result, what's my coefficient? 0.1175. Is it statistically significant? No, it's not statistically significant. So I can conclude that there is no heteroskedasticity in the result of me estimating log of y as a function of x. So what that means is that my result is saying that after I've estimated, okay, the coefficient of the intercept is minus 7.27. All right. The coefficient of the log of x is 0.11, and it is not statistically significant. So what does that mean? So I go back to my whiteboard. Okay. It therefore means that ln error term at square is equals to, okay, minus 7.27 plus 0.11 ln xt. And this 0.11 is not statistically significant. So I conclude there is no heteroskedasticity. That's PAC test. PAC says estimate ln error term square is equals to beta 0 plus beta 1 ln xt. Remember, that's our first assumption. And if beta 1 is statistically significant, there is heteroskedasticity. But if it is not statistically significant, there is no heteroskedasticity. Okay? Any question? That's PAC test for you.
Now, how do you get the not
You said?
the beta not the first beta? That's intercept.
Sorry, I can't hear you. Please, can you
I said,
say?
how did you get the intercept?
No, the intercept is from the equation now. The equation I estimated, this is the equation. The intercept is my constant, that's C. In EV, it's called C. That's
Oh,
C. In EV, it's called C, that's C. Okay? Somebody is asking, okay, Sir, just to be sure, do we still have to log the error term after we logged before estimating the model? Before estimating the model, we only logged y. Before estimating the model, we only logged y and x because the values are large. They might give you value, you might have values that are not large. You don't need to log. You estimate. When you estimate it, you get your error term. Remember, we got the error term when I show you the formula by crude method, normal calculation using calculator, minus and times. You get the error term. When you've gotten the error term, okay, the next thing you do now is square the error term. When you square the error term, you linearize, log the error term. So it is that log of error term that will now become your dependent variable in the second model, and then you solve. Any question on that? Lawson, yes, please, what's the question?
So you said by logging the error term after we've squared it. That means that we find the summation of the whole error term.
No. You know, your error term will have, there is a data point now, mu t at. You know,
Yes,
it's a
sir.
data point. The first thing is create another table where you will square it. You know, you start multiplying, times it by itself. The way you have your x square now, when you create that table, the next thing is that table you have created, linearize it. That's press lin. That's your natural logarithm 2.718. Linearize it, press lin something, lin that data. That's, you press your calculator. Now I know your calculator. You go to your calculator, you have lin ln, press it, and then it gives that data. It is now that data that will become your dependent variable in the second equation you are estimating.
Okay.
And it will still be a function of your x, your log of x you used. So it's only log of x you are using both at the first equation you estimate and the second one. Okay. Yes. Bolaji. Yeah, Bolaji.
Good morning, sir.
Yeah, good morning.
For the pack test, is it limited to just one independent variable?
Yes. Pack test is limited to one independent variable.
Okay.
So
And
pack test is
second question.
assuming that they are just two variable regression.
Okay. And the second question is for the graphical method, you said we'll plot the u cap square against y hat. And what is like the significance of plotting u cap square against y hat, or
You say
like
we
for
plot,
the
I don't
pack,
understand. You say what?
like for the graphical method, you said we'll
Yeah.
plot the error term squared against the fitted y,
Yes. Okay.
right?
Yeah.
And for a pack, we are using log of the error term squared against the independent variable, the log of the independent variable. Is there any like significant, can we plot the square of the error term against the independent variable, or
Okay.
one of
Yeah.
the independent
Yes.
variables?
You know that test precedes test.
Okay.
They first of all discovered chloroquine before amala. Amala is no more working. Artesunate. Artesunate is not working. Leonat. You understand? So
Yes,
the
sir.
first thing people used to do before was just to plot a graph. But people have said that, remember, in your econometrics at the introductory state, there was, I've told you that the difference between regression and causation. For the fact that a graph, something shows you a relationship, does not mean that something is impacting on something. Under the informal method, we only plotted a graph to show how they are co-moving. I go here, you go here. I go here, you go here. I go here, you go here. That's it. Regression is only showing, oh, Wizkid and Burna Boy, they did a collabo. Two of them sing song. That's graph. But you don't know who actually told the other, let us sing. Whether it is Burna Boy that brought a song and say, oh, the Wizkid, let's do this song. Or is it Wizkid that said, Burna Boy, we can do this song. So you don't know. All right?
Okay.
So
Okay,
the
sir.
second test, which is PAC, conducted a regression to see impact. So under the second one, which is PAC. Under the second one, which is PAC, PAC did an impact analysis, which is stronger than just plotting graph.
Yes, sir.
It's just like plotting a graph of GDP and GDP and GDP and my income, GDP, Nigerian GDP, and my income for the January to December. They might be moving the same direction. That does not mean it's that GDP that made my income to grow. Are you following me?
Yes, sir.
All right. Any other question? Somebody said I should please display. Sir, if you don't call. If a probability value is less than 5%, you conclude that it is statistically significant. And if it's greater than 5%, you fail to reject the null hypothesis. And then, or if your t-statistic is greater than 2, is your normal rule of thumb. That way you use to check for statistical significance.
Okay, sir. Thank you.
All right. Okay. So let's look at Glacier's test. Glacier was a bit, was a bit mechanical. All right. And what Glacier just said was very, what did he say? Glacier just said, look at Glacier. I'm opening your Gujarati. So look at what Glacier said. Glacier said, don't square your error term. Rather, estimate it as a function of either x. Don't even link your x. So have you seen it? The difference between PAC and Glacier. You must know the difference. So in PAC, you linearize and square the error term. But in Glacier, you don't linearize, you don't log it. 1, you don't square the error term. 2, rather, you find the absolute value. That is, ignore the negative signs. And don't square the x, don't log the x. Have you seen the difference between the two? I need somebody to answer me.
Yes, sir.
So that's the difference between the two. So Glacier provided different alternatives, estimate it with the square root of x, check it with the inverse of x, check it with the inverse of the square root of x, test all of those ones. Any one, by the time you test all of them, if none of them is statistically significant, you can say there is no heteroskedasticity. So note the difference between PAC and Glacier, the difference between PAC and Glacier. So we can just do one of them, still using our Excel. All right. Oh, somebody said I should share the Excel sheet again then. Oh, I'm sorry, but I'm sharing now. Still using our Excel. This is our X now. Okay. All right, this is our X. Remember, it's saying do not log the X. Okay. This is our no. You know that the X here. Oh, okay. Okay. Do not log the X. This is our X. Here's our error term. This is our error term. So I will copy, I can insert a new. Oh, there's a copied cell. Let me undo. So I can insert, all right? So all of these should still remain all of this, okay? But for this one, it should just be equals to -1 times this to eliminate these negative signs. And then all this one should be equals to these ones. So this is the absolute. Have you seen it? So this is the absolute, okay? So this is absolute of the error term. Absolute of the error term. That means ignoring the negative signs, Abi? Absolute of the error term, ignoring the negative signs. So I remember that when I estimated my model, the X there already was logged. So I'm going to use that log of X. All right? So I don't need these two. I only need the absolute of the error term and log of x because that x was already logged. Then I take it to my Excel environment, my normal e-view, sorry, e-views environment, and then okay, take it to my e-views environment, and then all right. So all I need is absolute of error term, absolute of what? Error term, all right, absolute of error term, the constant, and then ln x. That x is already logged before I estimated my model, so that's why. So look at it now. You can see that the coefficient again positive, but it's not statistically what? Significant. So we can conclude that there is no auto correlation. There is no, sorry, heteroskedasticity that is associated with the what? Regression result. So for Glacier, it's just an extension of PAC, but just as in Glacier is saying, do not find the absolute values, one. Two, you can now use the values like that or the square root of x. Okay, so all other
I have to stand up. Wait, I have to stand up here.
all other somebody should please mute yourself, please. The second one that says
Sir, sorry, sir. Please, what's your conclusion?
there is no heteroskedasticity because that coefficient is positive, but it's not statistically significant. It must be statistically significant for you to conclude that there's heteroskedasticity. So you can also you can oh, are we together? Are we together?
Yes,
Yes,
sir.
sir.
Yes, sir.
Yes, yeah.
Okay. So you can also do for others. I wouldn't waste my time, of course. For the other one, please mute yourself. For the other one that says square root of x, that will be equals to what? This abi raised to power 0.5. That's square root. Abi, if you square root it, that is it. That's for this. So you can test for this. The other one says 1 over inverse of x, which is equals to 1 over this. That's for the other one. Abi, that's for the third model. You test for this. All right. The other one says 1 over square root of x. So that's how you follow it. So you can test using this, test using this. You might also get the same conclusion. That is for pack test. Okay. Then the last one I want to now do, there's also Spearman rank. Okay. You can also use that. But the last one I want to do is Goldfield and Quant test. Goldfield and Quant test. Goldfield and Quant test. Okay. I'm sorry. I know we are getting close to 2 hours. Please, I'm sorry about that. Goldfield and Quant test. Under Goldfield and Quant test, Goldfield developed different approaches. Okay. And there are steps that we must follow under Goldfield. Steps that we must follow. Okay. For Goldfield. Goldfield, let me share my screen. That's Spark, this Glacier. I didn't want to use too much of oh, sorry. Goldfield, Goldfield and Quant developed different tests that we need to use, okay? So the first thing Gofield said is this, Gofield and Quant. Gofield said we order or rank the observations according to the values of X, beginning with the lowest value. The second thing Gofield said is omit a central observation where C is specified and divide the remaining two observations into two groups, okay? And then we fit an OLS regression for the first one as well as an OLS regression for the second one, okay? And then calculate the residual sum of squares for the two. Okay, so the first step is for us to order our observations according to the size, all right? So I will go to my Excel. And what are my observations? My observations are the error term, okay? And the what? The error term and the ln X. So I copy the two, take it to another Excel environment so that I can be exact. This is the year 1981, 1982. All right. Okay. So I've done this. I've gotten my data. The principle there says I should do what? Order or rank the observation according to the values of what? X. Order or rank the observations according to the values of what? Of X. Okay? So what do I do next? I'll go to my eViews. No, my Excel now. I'll go to my Excel. All right. So from my Excel, I have this. So remember, the law there is saying that I should order my observations according to the values of X. So this will be coming to this place because I want to rank these values according to the value of X. So look at it. I arrange this series according to sort them according to the smallest to the largest. I've done it. Look at it. So the smallest here is what? 22.9. The largest is what? 29. So I've arranged. Remember, I did not arrange my error term. I arranged my X. Then error term will follow. Are we following? Are we there?
Yes, sir.
Yes, sir. Yes,
Yes,
sir.
sir.
I did not arrange my error term. Error term is like twins. Anywhere you are going, I will follow you. I only arrange my X according to the size of X. Then what if, for example, now 22.98 is the smallest. What was the error term there? 0.15. I did not rank my error term. Just like when you've entered results, they've done exam finish, you put in the scores on the Excel. It's not according to matric numbers, you just type their matric numbers according to how they did the exam. But each of them have their score by their side. At the end, you now arrange the matric number according to where according to a matric number. Those are 001 will start 002. Under that scenario, you know that I wouldn't say because 001 is the smallest, you will score the lowest result. I hope you know that. I will match it with what? With the result that 001 scored. Do you understand that?
Yes, sir.
So that's the scenario there. So I've matched it. The next thing says I should delete the middle number. Now my series are from where? 1, 2, 3. Let me calculate. That should be 30 years. My series are 30 years. No, 39, sorry. My series are what? 39 years, okay? Then according to Monte Carlo says, if my series are about 30, I'm to remove a central number, which is 8, all right? Remember, my series now is what? 39. 39, assuming it is 40, 40 divided by 2, that's what? 20, okay? So that means the first 20, the first 15 series, for example, this is the first 15 series, okay? I can shade, this is the first 15 series. I'm dividing this series into 2. Then 39 to 40, 40 minus 15 should be 35, Abby. The next 15 series, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, Abby. 15. This is the next 15 series. All right, this is the next 15 series. So that means this is 15 up, all right, 15 down. Am I correct? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Nobody's even telling me that I'm not correct. 15. Okay, so this is the middle number. 1, 2, 3, 4, 5, 6, 7, 8. So this 8 is the middle number. So I might decide to give this one. So since it's 8 and I have 15 up, 15 down, the next step says I should eliminate this middle number. What will I do? I will eliminate it. After eliminating it, it says I have formed 2 different series. This is the first one and this is the second one. So the first one is lin xt. Let me call it lower, okay? And it goes with the error term lower because they are the smaller ones. This is lin x upper. That's the larger one. And then ut upper. So what has happened? That means I now have 2 different what? Series. I've broken down that series into 2. The first one will have lower values because I've arranged them. The second one will have what? Upper value. So I have done step 1, step 2. Step 3 now says I should fit separate regressions to the first one as well as another regression to the second one. So the first one I'll fit a regression is, remember, it is LT, the error term lower, as a function of X. I'll fit the regression, generates the RSS. The second one is I will fit this regression as a function of X, generates the RSS. So I will call this RSS1. I will call this RSS2. So how do I do it? I take all of this to eView Excel, to eViews now. Okay. Remember, it's from 1981 to 1995. That's just it. I take it to my eViews, 1981 to 1995. So 1981 to 1995, so that I can paste. All right. So yeah. So I have those 2 for lower and higher. So let me estimate the first one first. Which one is the first one? Lower. And that is lin x, lin, no, sorry, that's ut lower. Abi, ut lower, all right, as a function of x, okay, as a function of c, as a function of lin x lower. So this is the first regression. This is the first regression I'm fitting in. I estimate. I will generate the residual sum of squares. Residual sum of squares. From this result, you will see this is my R square, adjusted R square, standard error of regression. This is the sum of squares residual. So this is my residual what? Sum of squares. Residual sum of squares, 0. What? 0.20264. So I will paste it in my what? In my my Excel. This is the residual sum of square for the lower one. I'll paste it. That's it. Then I will also do for the other one. Okay. I will also do for the other one. Then for the other one, I estimate. Under that case, it is UT upper. UT upper. Okay. Against ln X XT upper. All right. And I estimate. For that one, this is the residual sum of what? Squares. That's RSS2, residual sum of squares. I hope you know what a residual sum of squares are. You know, they've taught you. They've taught you. Don't say they did not teach you. This is the second residual sum of squares. So I have divided my series into two equal parts, estimated the RSS of the first one, estimated the RSS of the second one. Okay? Now, it has a degree of freedom of n minus c minus n minus c over 2 minus k. That's the degree of freedom. N minus c over 2 minus k. So, this is what I'm saying. Those series have a degree of freedom of d of f is equals to n minus c over 2 minus k. What is n? N is what? 39. I've been 1981 to 2019. What is c? My c was 9. Remember, it was 9 I omitted. What is k? K equals to what? 2, number of parameters. So that means degree of freedom is equals to what? 39 minus 9 over 2 minus what? 2. Okay? If that is the case, 39 minus 9, that's 30. Okay? 30 over 2, 15. Okay? 15 minus 2, 13. So that means my degree of freedom is equals to what? 13. So if that is the case, the next thing says I am going to do what? Fit in and find my lambda. Lambda is equals to RSS2 over the degree of freedom over RSS1 over the degree of freedom. Remember, the degree of freedom are what? 13, 13. Okay? So I will need to find this particular formula in my what? Excel. Okay? So if that is the case, how do I find it? I go to my what? Excel. So remember, my degree of freedom is what? 13. Degree of freedom for the other one is also what? 13. Okay? So my lambda is equals to what? Remember, RSS2 over degree of freedom, close the bracket, over RSS1, okay, no, open the bracket now, over RSS1 over the degree of freedom, close the bracket. So my lambda is 4.83. That's my lambda. My lambda is 4.83. My lambda is 4.83. My lambda is 4.83. Then my lambda is approximated to an F distribution. F. I taught you F distribution in year 2. F statistics. My lambda is approximated to my F what? Statistics. Okay. Once this F statistics is statistically significant, I will conclude that there is heteroskedasticity. But if my F statistics is not statistically significant, I will conclude that there is no heteroskedasticity. That's my decision. Remember, our F statistics always have upper degree of freedom and lower degree of what? Freedom. So from that lambda formula, my upper degree of freedom is 13. My lower degree of freedom is 13. My F statistics is 4.833. 4.838. So I will simply go to my what? My table. Remember, I will simply go to my table That's my Gujarati. Go to my F statistics. That's the end part. End part of my F statistics. F statistics. F. Okay. F statistics. Okay. Remember, upper degree of freedom is 13. All right. Lower degree of freedom is also what? 13. So it's 13 under 13. That's what I'm looking for. But this one ends at 12. 1, 2, 3, 4, 9. Okay. So that means it must be in the next table. 12. And where is 13? 11, 12. And 13 is missing in this one. No? 13, 13. The upper degree of freedom is 13. Lower must be 13. So it should be 13 under 13 now. Why is 13 missing? Let me check for an F distribution from the Google. Okay, it does not have 13. So that means I will use 12 as an approximate since it does not have 13. Since it doesn't have 13, I will use 12 as an approximate. So now this is F distribution, okay? Then remember, the lower degree of freedom is 13, okay? So I would, let me highlight. The lower degree of freedom is 13. Then the upper should be 13, but because there is no 13, I'm going to use 12, all right? Remember, I'm testing at 5% level of significance, okay? So I'm tracing this 5% down to here. Look at it. So that means my F critical is 2.6. My F critical is 2.6. My F critical is 2.6. Okay, so I've gotten that. My F critical is 2.6. Okay, then my F calculated. So my F critical is what? 2.6. The F calculated is what? 4.8. So because 4.8 is greater than 2.6, what happens? You conclude that there is what? Heteroskedasticity. Because the statistics is greater than the critical value, and you therefore reject the null hypothesis of homoskedasticity, and then we assert the what? Alternative, that there is heteroskedasticity. So what did I do again? Let me explain. First of all, estimate your y is a function of x. When you estimate your y is a function of x, you generate your error term. When you generate your error term, you save it, you keep it. Then you bring your x values. This is your x values, okay? Your x values and your error term. Those are the two. But what do? You divide that series. You first of all arrange them either in ascending order or descending order, anyone you choose. But it's advisable to first of all arrange them in ascending order. All right. That is the best thing to do. Okay. Either you arrange them in ascending order or the descending order. But the person is arranging them in ascending order. So when you arrange them in ascending order, the next thing is you look for a central observation, C, that you would delete from the middle. Then check I will send you the note. You will see what Monte Carlo suggested that you should use. Get those ones, delete it from the middle. When you now delete them from the middle, you are now having two equal data points. For the first one, you estimate the model. Error term is a function of x. That's the lower one. Generate your RSS. Call it RSS1. For the second one, estimate the model for the bigger one. When you estimate it, generate the error term, generate the RSS and save it. Then fit in your F statistics. F statistics will always be equals to RSS2 over degree of freedom all over RSS1 over degree of freedom. That's 4.8. After you have done that, then you look for the F critical. Remember, at 5%, your degree of freedoms are upper and lower. Go and check the value. That gives you the value, and you can now conclude. Yes, so let me check the charts for the question before I attend. Okay. Okay, so somebody has helped to show the TSS. Alright, thank you, Jerry. TSS, ESS, RSS. You can get your RSS from there. All right, so okay, okay. Um, so what level of significance are we using for F? 5% is always the normal way. The graph I have excluded 13 and moved to 15. Yes, so there is no 13, 14. I checked on internet now too. So you use the closest, which is 12. That's for F statistics, okay? Yes, you are permitted to leave. You Ayodele said you have a class by 10. Yes, you can go for the class. Sir, for this test, the degree of freedom for both RSS will be the same. Yes, it will be the same. The degree of freedom for RSS will be the same. How did we get 13 as degree of freedom? N minus C over 2. Then all of them minus K. N is 39. Minus C, we omitted 9 variables. 9 data points at the middle. So C is 9. That's 39 minus 9. That's 30 over 2. That's 15. Minus K. K is 2. Minus 2. That's what? 33. That's 13, sorry. When we want to obtain RSS, do we take the error term as y when solving? Yes. Not the error term in the first y, but the error term, and you take the error term as y when solving. Correct. Yeah, correct. But sir, RSS is 1 over 1 minus ESS over TSS. Yes. RSS is 1 minus ESS over TSS. In the case of multiple regression, which of the independent variables do we rank the errors? Now, under this, yeah, this is a beautiful question. In the case of multiple regression, you choose the independent variable based on one, the degree of correlation between that independent variable and the dependent variable. Remember, you first of all do a correlation matrix to see the degree of relationship. So choose the one that has a higher degree of relationship, because that one best explains the movement in the model. 2, by intuition, by theory, you can also get your answer from that particular behavior of variables. You can look at those variables and conclude that, oh, this one might exhibit a similar pattern. So you can get it from there. Yes, okay. So now, yeah, Temidayo, question. Temidayo, your question. You raised your hand. Okay, nobody's raising hand. Comfort, do you have a question? Comfort, I can't hear you. Solomon, can you hear me?
I can hear you, sir.
Okay, so Comfort, I can't hear you. Okay, any other person has a question?
Sir, I have a question.
Okay.
Okay, so when you say we should estimate our RSS,
Please, 2 people are unmuted. 1 person should unmute, please. Who is talking? Comfort, are you the one talking?
no, is Elizabeth.
Okay, okay, let me mute Comfort. Okay, Elizabeth, yeah, what's your question?
Okay, when you say we should estimate our RSS1 RSS, do we solve it the normal way we estimate models? Like we get our intercept and slope.
Yes,
Then
yes,
after so we get our y at. Then
yeah, yeah,
start to get our RS.
yeah.
That's
And
the way we solve it.
yes, and you square it and sum it. Yes, you square that error term because that's the residual sum of squares. You square it and sum it. Yes.
Okay, okay, that's number one. Then number two is that how do we know the C, that is the number of items we want to omit? Is it by intuition or we are going to be given?
Okay. Um, if it's an exam, I can give you because I can give you C, tell you to find degree of freedom. I can do anything I like. Oh, sorry, I'm not going to do anything I like. I can ask questions in different ways. But in standard econometrics, Monte Carlo and somebody, I think it's in Gujarati, it's also in H. Green, Robert H. Green Econometrics. They suggested a standard to be used. The one in Gujarati said if n is between less than 30, use c equals to 8. And if n is above 60, use 16. Check from the Gujarati. There's always a standard given that you can use within that range. But that is not limited in the exam. I might not be expecting you to cram those standard. I can also expect you to cram the standard, and I might also specify the standard I want. Has that answered the question?
Yes, sir. Yes, sir.
Okay. Abubakar, what's your question? Nobody. Okay. So okay, yeah, I will share the note on how to eliminate the center. If somebody says 60 is 10, yeah, check. I think it's there. In case of the number of this is made and start, okay. I've answered that, I've answered that, I've answered that, I've answered that. So no question on that, Abby. Okay. Are we clear on that?
Yes, sir.
Okay, so let me just do the
Yes, sir.
final one. The correction, how do you correct for heteroskedasticity? When you have heteroskedasticity, how do you correct for it? All right, you do what we call a transformation. Okay, a transformation of your model. Transforming your model, okay. Um, we still have other method of heteroskedasticity. I wouldn't want to disturb you. I have that first three we've done is okay. We have rank and the rest, okay. So the first thing we do is to do a transformation. But we must first of all understand one, we assume, okay, that the factor that causes the heteroskedasticity is known. That variance causing the heteroskedasticity is known. We must first of all assume that. Okay, let me show you what I mean. We must first of all assume that what is causing heteroskedasticity is known. That's our first assumption. Okay. Remember that when we have heteroskedasticity, we say that the variance of the error term is not constant. That means we have one variance of the error term that might be 4 for the first sample, another variance of the error term that might be 6. Other variances of the error term might now be 4. Other variances of the error term is 4. Other variances of the error term is 4. That means from my analysis of giving 5 researchers, researcher 1 variance is 4. Maybe the person we are studying the income pattern of undergraduate students that are Christians, all those Christian people that like Christian, they have lower income is 4. Maybe this researcher 2 study the income pattern of the Muslims, all right, maybe they have lower income, the same thing, 4. This researcher 3 study the income pattern of those that are staying in hostel, and maybe because those that are staying in the hostel inside school, they don't really have money, that's why they are staying inside school, and so they have similar lower pattern too. Then maybe this other person study the income of people that are living in the suburb area. You ask them, oh, where are you staying? Ajegunle, Ilaje. So maybe those ones also have lower income. Then this person is now the one that studied the income of those that have uncle, uncle, auntie, and auntie. That means the variance of this person is 6. It then means that why this particular variance of the error term is not constant is because of this 6. This 6. If not of this 6, it should have been what? 4. So what is causing that heteroskedasticity is the variance of this particular sample that gave me what? 6. So you first of all have an assumption of the first one that you know the variance that is causing the heteroskedasticity. So assuming you know it, which is 6, the law states that you transform that particular model by dividing the model with the square root of that variance 6 that is causing the heteroskedasticity. So if I have this model and then I know what is causing the heteroskedasticity, which is 6, divide the model by root of 6. Divide the model by root of 6. So what am I saying? To do that, it means my yt is equals to beta 0 plus beta 1, okay, x, okay, t. For me to resolve the heteroskedasticity, all right, I assume that I know the nature or what that causes the heteroskedasticity. If that nature that causes the heteroskedasticity is related to a function, remember, why I got 6 in that particular variance is because the income of those group of people is high. So my model might just not just be to examine the impact of consumption of income on the spending pattern of undergraduate students. My model might also include, consumption is a function of income, age, family, all of those other variables. But why that model is heteroskedastic is because of that income is large. That means that the heteroskedasticity follows a pattern of that income. And it might be because it's as large as being the square of normal income of people. I can now say that the heteroskedasticity formed, all right, is equals to the one that is almost skedastic times xi square. I can say this is the pattern of the heteroskedasticity, where x is the income of those people that are in the large, that have a large income. And maybe because that income is square of the regular people's income. So if regular people are collecting maybe 200 naira or 500 naira per day, those ones, they are spending 10,000, 8,000. That means it's like square of the regular income of the people. For me to transform this model so that it will be free from heteroskedasticity, I will divide the model by square root of xi square. If I divide that model by square root of xi square, that means I will divide it by what? Xi. So that my new model, all right, becomes, yt over xt is equals to beta 0 over xt plus beta 1 xt over xt. That means my model is now yt over xt is equals to beta 0, 1 over xt plus beta 1. What has happened? Xt has cancelled xt. The beta 1 is no longer the slope. It has become the intercept. And then beta 0 has become the slope. and then I have 1 over xt, okay? That means this particular new model that is transformed is called the generalized least square or weighted least square. This model is now free from heteroskedasticity. The model is free from heteroskedasticity. The model is free from heteroskedasticity because the former model that causes heteroskedasticity is this. The former model that causes heteroskedasticity is this. Look at it. Okay? While the other model that causes without heteroskedasticity is this. So this new model has been what? Transformed. Okay? You can check from your Gujarati and see that you can prove that this model is free from what? Heteroskedasticity. So I think I would stop there. We've exceeded time. Any question? Any question? Question. You put no more here.
Yeah, yes, sir.
Oh, question. No question. Okay. For the
Sir,
okay. Yes, sir.
uh, sir,
I can hear you, sir.
my question is that under the assumptions of the heteroskedasticity, other Goldfield and Quant test, you say that the observation must be at least twice as much as the parameters to be estimated. What do you mean by that, sir?
I can't hear you. Say it again. You say what?
Observations must be at least twice as much as the parameters to be estimated.
Of course, now that is your number of observation. Your n must be at least twice as
Yes,
much as parameter. How many parameters are you estimating? 2. So what they are saying
two.
is that n must be at least 4. Your
Okay, sir.
your data span must be at least 4. At least 4. So 2, then 4, because your parameters are 2. And if you estimate like that first model we estimated that is about 8 parameters, that means your observation must be at least 16.
Okay, sir.
Yeah. Question.
Yeah.
It's only these 3 people have been asking questions. Comfort, Elizabeth, and Abubakar. Comfort, Elizabeth, Abubakar. Drop your matric number now on this platform. Comfort, Elizabeth, and Abubakar. Only 3 of you.
Yeah,
Type your matric number.
Bolaji has been asking too, sir.
Oh, you have started again. Comfort, Elizabeth, and Abubakar. That's what I said. Abubakar, yes. Comfort. And they are the only ones that comfort. Akonde, are you not dropping again? Or you cannot type? No. Okay. Oh. Is there another person that used to ask question? Nobody now. There's only 3 of you. Who else asked question?
Kashama Dupe.
Oh, yes,
Now, me,
yes,
I used
yes.
to ask
Kashima Dupe,
questions.
yes. Kashima Dupe. Hey, no noise, no noise, no noise, no noise. Mute yourself. Mute yourself. Yes, Kashama Dukbe, please. Yes, yeah, that's good. Any other person? Nobody else ask question.
Bolaji.
Bolaji, sir.
Yes, Bolaji. Talk. Let me see you.
Sir,
You only asked once, bro.
Yeah.
I've been able to do some justice to this concept of heteroskedasticity. Okay, and thank you for that.